PDB files frequently require changes in protonation state. Manually ensuring that each residue has the correct hydrogen count is tedious and error-prone. In this demo, we'll show how to prepare a PDB file with a realistic protonation state at pH 7 using the PDB2PQR server, read a PDB file containing amber force field residue names, and generate a hexagonal membrane system for simulation with the amber force fields. Note that we are using the PDB2PQR server in this example, and there are other servers that do similar jobs. The PDB ID 6IYC is a large membrane protein complex and does not have any hydrogen atoms, which is the case for most PDB files. First, go to RCSB, type in 6IYC, and click the Download PDB link. Next, click this link in the video transcript to go to the PDB2PQR server. Choose Upload a PDB file, and find the PDB file for 6IYC. Change the force field option to amber and the output naming scheme to amber. For compatibility with CHARMM-GUI, we also need to select the Keep Chain IDs option. Make sure that the pH is 7 and the PROPKA protonation method is selected. When you click Submit, the PDB2PQR server will begin running your task. If you entered everything correctly, after a minute or so, you should get a message saying that the conversion is complete. Download the 6IYC PQR file, then go to the CHARMM-GUI input generation section and choose Membrane Builder. Upload the PQR file we just generated. Make sure the PDB format says PDB and click Next. We want to keep all of the chains in our model. Here we see that PDB Reader detected the correct protonation states because it was able to process the amber naming scheme. One key difference between the CHARMM and amber force fields is that most protonation states are handled by patches in the CHARMM force field, but the amber force field uses different residue names for different protonation states, like ASH for protonated ASP. So leave all of the renamed residues at their suggested values. Note that CHARMM-GUI will convert each protonation state to proper amber residues if you choose to use the amber force fields. What we are actually missing in the PQR format, though, is the disulfide information. For this, we can open a new tab and go to PDB Reader and type 6IYC as the original PDB file contains the disulfide information. Clearly, the PQR format does not properly support N-glycans, which we will talk about later. When we click Next, we see that there are 4 disulfide bonds in chain A, 50 to 62, 140 to 159, 230 to 248, and 156 to 620. So we need to add these back in our PQR file reading. If you want to cap the terminal groups, you can use, for example, the ACE N-terminal patch and the CT3 C-terminal patch. If you're not familiar with the CHARMM terminal patches, please click this question mark to see the meaning of each patch. Again, note that CHARMM-GUI will convert each patch to its proper amber residue if you choose to use the amber force fields. For N-glycans, there are several options. First, we can build them based on the sequence from the PDB Reader page that we saw using the original PDB file, or alternatively, we could use the original PDB file and change the protonation state based on the PDB Reader page using the PQR file. In this demo, we will simply ignore N-glycans since we already cover how to model glycans in the video demos for Glycan Reader and Modeler. Once everything is correct, go to the next step by clicking Next. Now the protein needs to be oriented in the membrane. Rather than manually specifying the rotation and orientation options, in this demo, we simply use the ppm server to find the orientation for us. Click Next to orient the protein. When the lipid options page loads, make sure to view the structure to ensure that it was oriented properly. The placement looks good, so we'll continue. In this system, we'll generate a pure POPC bilayer. Since we said we wanted a hexagonal system, we need to select the hexagonal system type. Then choose the Ratio of Lipid Components option and use 125 angstroms for the X and Y length. And for POPC, put 1 and 1 for the ratio in the upper leaflet and in the lower leaflet. Click Show the System Info, then click Next. Since this is a large system, it will take a few minutes to finish packing the lipid pseudospheres. Now would be a good time to save the job ID if you haven't already. When packing finishes, view the Step 3 packing PDB structure to make sure that there are sufficient lipids around the protein. We will leave the solvent options at their defaults. Click Calculate Number of Ions, then click Next. CHARMM-GUI will then replace each pseudosphere with a lipid molecule. Again, because the system is very large, it will probably take a few hours to complete. Make sure that you have saved the job ID so you can return to your job later using Job Retriever. Once the replacement step is finished, we can assemble all system components by clicking Next. On the Force Field Options page, choose the amber force field and check Hydrogen Mass Repartitioning, which allows us to perform the simulation with a 4 femtosecond time step. Then click Next to generate amber input files. Once inputs are generated, we can download all necessary files to begin our simulation.